Hey Chemistry, I'm working on some problems here. These are some problems I gave you on Monday, and I wanted to go over how to do them. Do realize that you are going to have a quiz on Wednesday, and this is not going to be anything like the homeworks I've given you so far. It'll be a quiz where you put in your number, and whatever that number is the number you put in. You don't get a chance to see the answers or anything like that. And I will grade it, go through and look at the answers. And like with the homeworks, we've been seeing a situation where like I might put 0.711 and your answer is 0.712 and the system says you're wrong. Obviously that's, it's very, very close. So in that kind of situation, I'm going to be looking through to see if answers are really close to the correct one. But there is a quiz on Wednesday on Schoology. We will have a handful of problems I don't know yet. Making this all online is a little bit more tricky than doing this on paper. So we'll see what happens. Probably about 10 to 15 problems or so. Some of them are very simple, like is this exothermic or endothermic, justify your answer, that kind of thing. But do be ready for a quiz on Thermochem, which includes MC delta T stuff, so like heat transfer and putting things in water, how's the temperature of the water change, those kinds of questions. Being able to figure out if a reaction is endothermic or exothermic, and then also being able to use this guy right here, the enthalpy of a reaction, the molar enthalpy. So let's go through the problems that I gave you on Monday. First one was this one. Hydrazine, N2H4, reacts with H2O2, that's hydrogen peroxide, to produce N2 gas and water according to the equation below. Here we go. And the enthalpy of the reaction is negative 818.23 kilojoules per mole. The first question is, which reactant is limiting? And this is a really simple question because we are told we have 100 grams of N2H4 and 200 grams of H2O2, and then we have to figure out which one runs out first. Essentially, it's just a basic stoichiometric question. So let's go ahead and do that. So 100 grams of N2H4. And remember, with limiting reactants, I have to take each of the reactants and take them to one of the products, and then compare the amounts that are made, and the smaller amount made of the product is going to tell me which of the reactants is limiting. So we'll start with this N2H4, convert to moles. Molar mass of this compound, I'll just round it. So nitrogen is 14, hydrogens are 1, so it's 28 plus 4, so 32. And I'll go to N2. So the ratio between those is 1 to 1. So for every 1 mole of hydrazine consumed, 1 mole of N2 is produced. So at the end of the day, this is just going to be 100. You kind of missed that right there. 100 divided by 32. So 100 divided by 32. 3.125. Let's just do 3.13. So 3.13 moles of N2. Little thing here. Take that off. There we go. And then do the same thing with the hydrogen peroxide. So 200 grams of H2O2. Convert to moles. Molar mass of hydrogen peroxide, that would be 32 for the oxygen, so 16 plus 16 is 32, and then plus another 2, 34. So 34 grams per mole for H2O2. And then we're going to convert to N2. So the ratio is 2 to 1. So we're going to divide by 2. Oops. 2 is the N, H2O2. 1 mole of N2. Okay, so again, we're just going to compare how many moles of N2 could be produced. So 200 divided by 34, and then divided by 2. And this is a 2.94 moles of N2. And this is a really good example. So a lot of you guys on the video, you just said, oh, well, there's less of one of the reactants, so therefore it's the limiting reactant. You didn't actually take it to the products and compare. In this case, this is sort of weird. There are 200 grams of H2O2, so there's double the mass of the other reactant, but the H2O2 actually runs out first. It runs out first because it is consumed at 2 times the rate of the N2H4. So only 2.94 moles of N2 can be produced from the 200 grams of hydrogen peroxide. So you always have to do the limiting reactant problem where you go to the product and compare how much product is produced. You can't just say, oh, there's less of this or there's more of this, and that's going to be, the reactant that's limiting, et cetera, et cetera. You have to do the math. You've got to do the actual calculation to figure out. In this case, your intuition would say, oh, there's 200 grams. That's double this much N2H4. So therefore, this is going to not run out first. Instead, this is going to run out first. But that's not the case in this example. In this case, the N2 that's produced is going to be less from the H2O2. H2O2 is the limiting reactant. So write that out. Okay. How do you justify it? You justify it with a calculation. And then last question here, how much heat would be produced? So in the question, they tell us that the enthalpy of the reaction is negative 818.23 kilojoules per mole. Okay? Now, we know that 2.94 moles of N2 are going to be produced. So I'm just going to go ahead and use that number off the bat. So 2.94 moles of N2 are going to be produced because I know that H2O2 is my limiting reactant. And I need to convert this mole value to kilojoules using the enthalpy of the reaction. I'll put a little RXN down there. So in one cycle of this reaction, 818.23 kilojoules of energy are going to be released. So if 2.94 moles of N2 are produced, well, then how much energy is going to be released? So we're going to convert this moles of N2 to moles of reaction and then ultimately to kilojoules. How do I convert to moles of reaction? Well, I look at my reaction equation. For one cycle, one whole run of this reaction, 1 mole of N2 is produced. So that's the molar ratio between N2 and how much reaction happens. So it's 1 to 1. So 1 mole of N2, move that up, to 1 mole of reaction. All right? And then for every 1 time the reaction occurs, every 1 mole times the reaction occurs, negative 818.23 kilojoules of energy are released. Okay? That's where I use this value right here. And then I do the math. All right? So 2.94 times 1 times negative 18.18.23, and my answer is negative 2405. Let's just round that to negative 2406 kilojoules. 2406 kilojoules. So that's how much energy is released when this much stuff is used in the reaction. Ultimately, the H2O2 runs out first, and we make this much energy from that reaction. All right, next question. A 10-gram sample of gold at 55 degrees Celsius is deposited into 200 milliliters of H2 at a temperature of 10 degrees Celsius. If the specific heat of gold is 0.129 joules per gram Celsius, at what temperature should both the gold and water be at the end of the experiment? Something to keep in mind here, whenever you've got some kind of hot thing put into cold water, at the very end, when all the heat from the hot thing is transferred to the cold water, the temperature of the thing you put in and the water will be at the same temperature. That's just kind of how things work. The hot thing won't be hot anymore. It's given its heat to the water, but the water is going to rise up in temperature while the hot thing cools down in temperature. And we're trying to figure out, well, what is the temperature of the water and the gold going to be at the end of this process? Well, here's what we know. We know that we have 200 milliliters of water, and we know that it is at a temperature of 10 degrees Celsius. We know that the gold going into the water has a mass of 10 grams, and its initial temperature is 55 degrees Celsius. Remember that we have the law of conservation of energy, which means that really at the end of the day, the amount of heat that the gold gives away. It's an exothermic process for the gold. It's losing its heat and giving it to the water. It's going to be equal to the amount of energy, the amount of heat that the water gains. And so what we can do is we can say, okay, well, MC delta T for the gold has got to be equal to the MC delta T for the water. And we know that delta T, that's final temperature minus initial temperature. We know that the final temperatures are the same. They have to be the same. That's how heat works. When the hot thing goes in the cold thing, the hot thing's got to cool down, and the cold thing's got to heat up, and they got to reach the same temperature. So we're going to make use of this equation, and TF is going to be the same on both sides, and we can do the algebra to figure it out. Let's go ahead and do that. So MC delta T for the gold is going to be 10 times 0.129 times, we don't know the final temperature, but we know the initial temperature was 55. This is an exothermic process, so it's going to be a negative value. It's losing its heat. The MC delta T for the gold is negative overall. Okay, and then MC delta T for the water, well, the mass of the water, we have 200 milliliters of water, so the density of water is 1 gram per mil, so we have 200 grams of water. The specific heat of water, you should have this handy in your brain always, 4.18. And then the final temperature, we don't know, but the initial temperature of the water was 10 degrees Celsius. All right, let's go ahead and do the math here. So 10 times 0.129, that's going to give us negative 1.29 times TF minus 55 equals, can't do that in my head, 200 times 4.18, okay, 836. These two numbers calculated here. 836 times TF minus 10, okay. And then we're going to distribute, so distributing to the things in the parentheses. So negative 1.29 TF minus, that's going to be plus though, because that's a negative and there's a minus there. So 1.29 times 55, 70.95. Okay, distribute here, 836 TF minus 8360, just multiplying by 10. All right, let's go ahead and get everything on one side that we want. So I'm going to do minus 70.95 over here. And I'm going to subtract 8360 over here. Okay, so minus 1.29 minus 836, negative 837.29. TF equals 8360 minus 70.95, negative 8430, 8430.95. I'm going to hold all these sig figs until the very end, and then go ahead and divide both sides by negative 837.29. You can see the negatives will cancel out. If you didn't put a negative here at the very beginning with the MC delta T for the gold, that would mess up the whole math. That would actually mess up everything, and you would get a number that doesn't make sense. I'm not sure off the top of my head what it would be, but when students forget the negatives, they'll get really weird answers sometimes, and then they'll put that on the test, and I always laugh. In this kind of situation, they'll get they'll get the temperature of the water goes from 10 degrees Celsius to like minus 30 degrees Celsius, and that doesn't make any sense. If you put a really hot piece of metal into water, it shouldn't go down in temperature. It should go up in temperature. That's just common sense. So when you're doing these kinds of problems, double check yourself and just say, okay, does that even really make sense? I just put a hot piece of metal in cold water, and then my calculation says that the water is going to go below freezing. That doesn't make any sense. So double check yourself always. Okay, let's go ahead and do this math here. So negative 8430.95 divided by negative 837.29, and I get 10.07. That's not very stupendous. That's the correct answer, though, 10.07. So the final answer, right there, 10.07 degrees Celsius. And you might be asking yourself, I just put a really hot piece of metal into cold water. Why did the temperature of the water only go up by 0.07 degrees Celsius? Well, a reminder, the specific heat of water is 4.18 joules per gram Celsius. It takes a lot of energy to raise the temperature of water. Remember, that number is how much energy in joules it takes to raise 1 gram of water by 1 degree Celsius. 4.18 is a huge number. It's really, really large. Water has one of the highest specific heats of all substances on the planet. So you took a 10-gram piece of gold, which is not very much, and it was at 55 degrees Celsius, which is not that hot, but not unpleasant, and you put it in water, and the temperature of the water only went up a little bit. So this actually does make sense, because water is really good at keeping its temperature without changing too much. It doesn't change temperature very easily. So 10.07 is the correct temperature. Next question. Sodium carbonate reacts with HCl according to the following reaction. So hydrochloric acid reacts with sodium carbonate, produces carbon dioxide, water, and sodium chloride, our favorite salt in the entire world. The enthalpy of the reaction is negative 143 kilojoules per mole. First question, is it exothermic or endothermic? That is a super duper easy question. It is exothermic. Why is it exothermic? It is exothermic, and if you don't know this right now, that's a bad sign. It is exothermic because the enthalpy of the reaction is a negative number. Exothermic reactions have negative enthalpies, meaning that the heat is released, it's lost, it goes away, it's taken away from the reaction and given to the surroundings. So it's an exothermic process because that enthalpy of reaction is a negative number. B, calculate the amount of energy released or gained, depending on what you answered here, when 25 mils of 0.186 molar HCl is added to excess sodium carbonate. All right, so what we're going to be doing here is say, okay, if I have 25 mils of this hydrochloric acid, okay, how much heat is going to be produced in the chemical reaction? And we can do this because we know the enthalpy of the reaction. We know it doesn't matter what reactant or product we're talking about, as long as we know how much is there, we can figure out how much heat was produced. Let's go ahead and do this one. So this is where we use molarity again. So remember, molarity is moles over liters. And so my molarity of this hydrochloric acid is 0.186. It's 0.186 molar. And I don't know how many moles that is, so I'll put X for it. And I have 25 milliliters of it, so it is a volume in liters of 0.025. All right? So 0.025 multiplied on both sides. So X is equal to, let's do the math, 0.186 times 0.025, 0.00465. I'll hold all the sig figs for right now. 0.00465 moles of HCl. Cool. So that's how many moles of HCl are going to react. And they tell us basically that this is the limiting reactant because, well, we have excess sodium carbonate. So the HCl's got to run out first. So let's go ahead and do the stoic. So 0.00465 moles of HCl. All right. And now this is the part where I'm going to convert from moles of HCl to moles of reaction. So how many moles of HCl are consumed in one cycle of this reaction? 2 are. So 2 moles of HCl are consumed every 1 mole time the reaction occurs. Okay, and then that is where I go ahead and use, next is where I use the enthalpy. So for every mole time the reaction occurs, negative 143 kilojoules of energy are released. So, whoops, there we go. So negative 143 kilojoules per 1 mole of reaction. And there's our answer here. Let's go ahead and do the math. So 0.00465 divided by 2, and then multiplied by 143. times negative 143. And I get a funny number, negative 0.332. So the answer is negative 0.332 kilojoules. If you wanted to put that in joules because you don't like the kilojoules with the decimal, you could say that's 332 kilojoules. Whoops, dang it. Joules, not kilojoules. Silly me. Because remember, there are 1,000 joules to a kilojoule. So if I wanted to turn that into joules, I just multiply it by 1,000. All right, next problem. All right, this is one where we talk about finding the enthalpy of the actual reaction. A 2.5 gram sample of sucrose, C12H22O11, was burned in excess O2 in a container that held 2.19 kilograms of water. The temperature of the water increased from 20.5 degrees Celsius to 25.01 degrees Celsius. Determine the heat of combusting sugar in kilojoules per mole. So in this question, it's not said directly, but you're being asked, what's this? What's the enthalpy of the reaction? And remember that enthalpy can be calculated using this kind of question here, or this kind of equation. It's Q divided by the number of moles of reactant. Okay, so remember Q is MC delta T. Okay, so we're going to make use of that. We're going to try to find the MC delta T for ultimately the sugar that's being reacted. Here's a diagram of essentially what's happening. Inside some kind of container with a bunch of water, that's the blue, there is a little cup, and in that cup is sugar, 2.5 grams of sugar. And the sugar is being reacted with oxygen, making a huge explosion. Heat is going out of that reaction. How do I know heat is going out? I know that because the temperature of my water goes up. My temperature goes from 20.5 degrees Celsius to 25.01 degrees Celsius. So I immediately know that enthalpy is going to be negative. I know that the reaction is releasing heat out into the water. So this is an exothermic process. Now, how do I figure out the amount of heat that was gained by the water? We have to remember the law of conservation of energy. Remember that the law of conservation of energy is going to tell us that the amount of energy that the reaction produced, which is being lost by the reaction, is the amount of heat that the water's gaining. I cannot directly calculate this value because I don't know the specific heat of sugar. But I can figure this out because this Q value out because I know the specific heat of water. So what I'm going to do here is say, well, since I can figure this out and they're equal to each other, I'm just going to calculate the Q for water, change the sign, and then I can go ahead and figure out delta H. So the Q for the water is going to be equal to the mass of the water. The mass of the water, 2.19 kilograms. I have the specific heat in grams, so this is going to be 2,190 grams water times the specific heat of water, 4.18 joules per gram Celsius, and then multiplied by the change in the temperature of the water. The water ended this at 25.01, and then it started at 20.50. So the amount of heat that the water gained is going to be equal to this here. So 2190 times 4.18 times 25.01 minus 20.5. Okay, so you can see my calculator. So 2190 times the specific heat times the change in the temperature. That's a pretty big number. So 41285. 41285. Now that answer is in joules. I want to convert that to kilojoules because enthalpies are always in kilojoules. So there are 1,000 joules to 1 kilojoule. So we're going to have this be 41 point, we'll do 41.29 kilojoules. Okay, 41.29. Now, this is how much energy the water gained. How much energy did the reaction lose? It lost, put that down here, it lost 41.29 kilojoules. Okay? So the enthalpy of this reaction, I want that in kilojoules per mole. How many moles of sugar actually reacted? Well, I got to figure out that in just a second. I'll put this here. So 41.29 kilojoules divided by how many moles of sugar reacted. Now there are 2.5 grams of sugar. Let me write this over here on the side. I'm kind of running out of room. I'm going to go ahead and divide by the molar mass of sugar. Let's just quickly do it in our head. So 12, carbons are 12, so 12 times 12 plus 22 for the hydrogens, and then plus 11 times 16 for the oxygens. So the molar mass of sucrose is 342. Show that there. The number of moles of sugar that reacted, 2.5 divided by 342, 0.0073. Okay, I'm going to put that down here. So remember, it's how much heat was lost by the reaction in this case divided by how many moles of sugar reacted. So 0.0073 moles. And that'll give us the enthalpy, the amount of energy released per mole of the reaction. So negative 41.29 divided by 0.0073, that's going to be this number, negative 5656. So negative 5656 kilojoules per mole. There we go. This is probably the toughest kind of problem you could encounter because it uses pretty much everything we learned. You're going to use every single thing that we've learned so far. MC delta T, you're going to talk about how energies are being exchanged between the two substances, between, in this case, a reaction. And then the law of conservation of energy is used. And then converting between grams and moles is used. Converting between joules and kilojoules is used. This is a pretty tough kind of problem. You should expect something like this on Wednesday. So hopefully got that down. Remember also the solutions are already online. So if you want to look in the assignments folder for thermochemistry, you can see the solutions worked out step by step there as well. So what mass of copper originally at 50 degrees Celsius must be added to 1 kilogram of 10 degrees Celsius water to raise the temperature to 20 degrees Celsius? All right. So this is an interesting kind of problem because it uses that law of conservation energy thing again, but we're going to be using it to figure out the mass of copper that would be needed to raise the temperature of this water to 20 degrees Celsius. So what we're going to do here is say, okay, I've got this water, it's 1 kilogram in mass, and I want to know if I wanted to get it from 10 degrees Celsius to 20 degrees Celsius, and I had copper that was 50 degrees Celsius, how much copper would I need to do that process? That's going to be a lot of copper, I'm sure. So first things first, if this water were to go from 10 to 20 degrees Celsius, how much heat would be needed? Well, we're going to do that using Q equals mc delta T. And at the end of the day, this is the exact same amount of energy that the Q for the copper is needed. Okay, so the Q for the water and the Q for the copper are the same, mc delta T. But we're going to switch, we're going to take the number here for the water, and then we're going to translate it over to the mc delta T for the copper. So let's do this in steps. So Q for the water, if my water had a mass of 1 kilogram, which is 1,000 grams, because the heat is 4.18 joules per gram Celsius. And if I wanted my water to go from 10 degrees Celsius to 20 degrees Celsius, how much heat would I need to do that? Do that math. So 1,000 times 4.18 and then times 10. So 41800. 41,800 joules of energy would be needed to raise 1 kilogram of water from 10 to 20 degrees Celsius. Okay. Now, that copper has got to give up, therefore, that much energy. So some amount of copper put into that water has got to give up 41,800 joules of energy. Let's do that. So Q of copper is equal to 41800 joules. Okay. And that's MC delta T. I don't know the mass of the copper. But I know the specific heat, 0.39. And then here's the next part that's a little tricky. So the starting temperature of the copper is 50 degrees Celsius. What's the final temperature of the copper? It's going to be 20. After the process is over, it's going to be the same temperature as the water. So its final temperature is 20 minus 50. You're going to see something immediately kind of weird about this. This is going to make a negative number. Remember though, this process for the copper is exothermic. It's giving its heat to the water. So I'm going to mark this down here. This energy is negative. It's being lost by the copper. So it's going to be a negative number. So let's just go ahead and do the math now. So negative 41800 equals, and then this is going to be M times all this over here. So this is going to be negative 30. So negative 30 times 0.39 times M, so negative 11.7. Negative 11.7 M divided by 11.7 on both sides. Okay, so the mass of my copper, I'll just get rid of the negatives there, so 41800 divided by 11.7. That's a huge number. That's a really, really big piece of copper. So 3572. We'll do 3573. There's our answer. Realistically, that would be a humongous piece of copper going into 1 kilogram of water. That's a liter, just 1 liter of water. So that's like, that much water. Well, it's exactly this much water right here. So that doesn't really make any sense because that's never going to fit inside 1 liter of water. But it's just a mental exercise kind of problem. Unless the copper was extremely dense, maybe that would work. Maybe. Anyway, that's the end of the problems. I hope you guys enjoyed this. These are the kinds of problems you will expect on Wednesday's quiz. This is everything. There might be some simpler ones where you just use the enthalpy and go do stoic, that kind of thing. But there are definitely going to be trickier problems like this on Wednesday's quiz. And like I said, you're not going to be able to put in an answer and see if you got an answer right and that kind of thing. And I know many of you are going to chit-chat about this, so these problems will be challenging. So you have to know what you're doing. And at the end of the day, if you guys work together and get the answers right, I guess that's okay with me. But don't expect them to be simple. Really. All right. Have an excellent day. I'll see you maybe May 1st. Maybe not. We'll see. All right. Stay safe. Wash your hands.